In the next part of lesson 4, we're going to look at one mean hypothesis test and demonstrate how companies can use them to help them make better business decisions. The company owns several cocoa bean farms. You want to distribute your cocoa beans in the US, but you are informed there are FDA standards that your product must meet. You read the FDA's Food Defect Levels Handbook to learn more about this process. You learn that you need to test for mold, insect filth, and what? Well, let's go ahead and open up the Food Defect Levels Handbook. And to make it go faster, I'm going to do Control F to find, and then spell cocoa beans. Okay, so for cocoa beans, you have to test for mold, insect filth, and mammalian excreta. You have to test for those three things. So let's put that right there. The first two food defects are obvious, right? Mold and insect filth, like bug parts. And sampling your production indicates that they are not problematic. So you have really low levels of the two, right? Now, you've never heard of the third food defect, the one that is in the answer box right there, right? So you did a Google search. In it, you came across this article. Control F. I searched for mammalian excreta. So what is it? Well, it looks like it's rodent poop, right? I don't know why they wouldn't just say rodent poop. I guess rodent poop is more disgusting than mammalian excreta. So there's rodent poop in your food. Now, an FDA defect action will be taken against your company if your cocoa bean samples average what? Let's widen this out to see if we can see it. There it is. If your cocoa beans average 10 milligrams or more of mammalian excreta per pound, then there's going to be an action taken against your company. Average 10 milligrams or more. So it can be equal to 10 milligrams, or it can be more than 10 milligrams. That includes the word equals. So that is the null hypothesis. To test this hypothesis, you periodically take a random sample of cocoa beans and use 10% level of significance. Each sample has 41 pound samples in it. The following is an example of what kind of test. Well, this says average greater or equal to 10 milligrams of mammalian excreta. And this right here says the average is less than 10 milligrams. This one here is the alternative hypothesis, and it has to be the opposite of the null. So this says the average has to be less than 10 milligrams. And when you're looking for the type of test it is, you're looking at the alternative hypothesis, and it's pointing to the lower tail of the distribution. So it's a lower tail test. It's a one-tail test, but not only is it a one-tail test, it's a lower tail test. Okay. Now, all the data is at the bottom of this problem. Now, we're sampling this distribution a lot, right? So this just happens to be one of many. So I'm going to grab defects per pound, and then I'm going to grab something outside the table, the S. I'm going to paste it right here. Highlight just the numbers. I'm going to label the cells, this object of cells. I'm going to label that defects. If I were to type equal defects over here, it would put a blue box around the number. So I've defined an object, and that object is the cells that contains our sample data, right? I grab these phrases. I'm going to put it right here. I'm going to paste as match destination formatting. To get the sample size, I'm going to type equal count A and then defects. So the sample size is in fact 40, right? Sample average or sample mean is found by typing equal average and then defects. That averages the values in our sample. The standard deviation of the observations is found by typing stdev.s. This calculates the square root of the variance of the observations. And then I'm going to type defects. The standard error, as we said in the previous part of this lesson, is the square root of the variance of the observations divided by the sample size. Now, the square root of the variance of observations, that is the standard deviation. And then we can divide by the square root of the sample size, which is 40 in this case, right? I'm going to come up here and I'm going to type hypothesized value. The hypothesized value, the standard that we have to meet as a company is 10. And those are milligrams, right? 10 milligrams. And the standard deviation is in milligrams too. The test statistic, we're going to first calculate the point estimate of the difference. And the point estimate of the difference is the sample mean. The sample mean is being used to estimate the population mean, right? We're using the sample mean to estimate this population mean. The sample mean is going to vary around the true value, right? If the sample is representative and random, right? So it's pretty close to 10. Now, the probability that it equals 10 is going to be 0 because the sample mean could take on infinite many values, and there's only one 10 on the number line. So the probability that the sample mean equals 10 exactly is going to be 0, right? So there's going to be a difference. Our question is whether the difference is significant. In this case, we want to know if it's significant and negative, right? So we're going to use a sample mean as an estimate for the population mean. And we're going to subtract off the hypothesized value, 10. This is the point estimate of the difference. It's negative. Why is it negative? Because the sample mean is less than the hypothesized mean. Now, in order for us to avoid an FDA action, this difference has to be significantly negative. It is negative, which means our sample average is less than the standard that we have to meet. The question is that difference significant? So there is a difference, right? Now, to calculate whether that difference is significant or not, we have to divide by the standard error. And then when we divide by the standard error, we get the test statistic, negative 1.95. The degrees of freedom are found by subtracting 1 from the sample size. Set these decimal places equal to the amount requested, which is 4. I'm going to go ahead and put them in here. So I'm going to be on hold for a second. All right, welcome back. I've entered these values in. We've got them all correct. Now I want to calculate the p-value. So in order to calculate the p-value, let's open up at distributions.com. We don't know the true population standard deviation. It's nowhere given. We don't know it. So we have to use a t-distribution. So let me click on the t-distribution first. The degrees of freedom are 39. The test statistic, the value on the number line, in this case, the test statistic is negative 1.9513. Well, we can only go to negative 1.95. And then this is saying we want the lower tail of the distribution. It's pointing to the left. So we want the left tail. So this is our test statistic. And that is the test statistic's p-value, the probability of being less than the critical value. We know it's going to be about 0.029, but we need 4 decimal place accuracy. So we know it's going to be about that. We're going to calculate it using Excel. And when we calculate using Excel, we're going to use the t dot dist or dot inverse. Well, we're going to plug in a number to get a p-value. So we want to use t dot dist. That means we have to feed in it a number on the number line, which is our test statistic. And then we need to feed it the degrees of freedom. And then we need to type 1 for cumulative. And that's going to give us a p-value. And the p-value to 4 decimal place is close to 0.029, but it's actually 0.0291. So it's really close to that, but we have to add a 1 there in the 4th decimal place, 0.0291. Now I'm going to move this around a little bit. The test statistic and the p-value go together. The critical value and the significance level, let me grab the significance level from over here. The significance level and the critical value go together. So these go together as these go together. Now I'm dividing alpha by 1 because it's a one-tailed test. If we're a two-tailed test, this would be equals only. This would be less than or greater than. And we'd divide by 2, but we're going to divide by 1 here because it's a one-tailed test. I have 10% significance. To find the critical value, visually, what do we got to do? I have to change this to the significance level. And I want to keep it on the left tail because it's a left tail test, right? Lower tail test. The degrees of freedom are still 39. Now the value on the number line is a negative 1.304. So we should get something close to negative 1.304. This is 3 decimal places from statdistributions.com. I want 4 decimal place accuracy. I'm going to type t dot inverse because I want to feed it a probability value. And areas under the distribution are probability values. So I'm going to feed it 10%. And then I need to feed it the degrees of freedom. And I get a critical value equal to negative, to 4 decimal places, negative 1.3036. I'm going to hit enter to make sure I got it right. The alternative hypothesis is pointing to the purple tail. The null hypothesis is pointing to the area around 0. That's the equal to part. And then it's pointing to the right. If the difference between the sample mean and 10 were positive, our test statistic would be on the right side of 0. It'd be somewhere here. Now, if that test statistic was out here, right, beyond 3, we would say the difference is positive and significant. If that test statistic were close to 0, between negative 1.3 and positive 1.3, if it's close to 0, we would say that difference is insignificant. If that test statistic were under the purple area, which is our significance level, then that difference would be negative and significant, right? So this means if the test statistic were, say, negative 3, then the difference is negative, and since it's under the significance area, it'd be a significant negative difference, right? Is that the case? The test statistic is near negative 2, right? Negative 1.95. So it is negative, and it's under the purple area, which is our significance level. It is negative and significant. It supports the alternative hypothesis. We can accept the alternative and reject the null. We're saying the average is less than 10. Why? Because we've overcame the burden of proof. The hump is the burden of proof. We've overcame it. We can say that our average is less than 10. So we are rejecting the null hypothesis, which means we've accepted the alternative hypothesis, right? It's okay to accept an alternative hypothesis because that involves evidence that overcomes the burden of proof. So we have evidence in support of the alternative hypothesis, which means less than 10 milligrams of rodent poop is in each pound of our cocoa beans, which means an FDA defect action will not be taken against our business. So we can continue to import our cocoa beans into the United States.